All right, 1 o'clock. How's everyone doing? 6 out of 10. I see that. Yeah, not a 10 out of 10, but maybe a little higher than a 6 out of 10. Are you all looking forward to the McKay lecture today? It's right after class. Anyone going?
Yeah, I'll stop by.
Nice. Yeah, it should be interesting.
It should be very interesting, actually.
Yeah. What's that?
Good topics of conversation.
Yes. Yep. No, it'll be fun. It's an annual thing. We throw this every year. We invite someone high profile to come in and talk about something interesting. So yeah, take a look at the flyer, see if you're interested. I believe it's at 2:30, so it's 15 minutes after class. So if you don't have class, highly recommend you show up for that. Should be good. So office hours are not tomorrow, not today after class. They are Friday, tomorrow, 11 to 1. So feel free to stop by. And I'm hoping to talk to each of you individually about your projects over the next couple of weeks. So you're going to be getting an email from me with some feedback on your project, but I also want to talk to you individually. So we're going to be doing more of this over the next couple of weeks, just so we can all sort of get on board with the projects we're working on, which should be fun. Hopefully this final project is not too stressful, but is like a fun project for you. So what we're doing today is essentially closing out part 5. This is essentially the end of direct discussion about the general linear model. We're going to move from the general linear model into part 6, where we talk about how to pull together like slides and written work to communicate findings. So some of this will involve how we write. Some of this will involve constructing useful visuals, which is a big part of what we've done in part 1 and 2. But we're going to focus on communicating findings. So this is how we write about our results and how we connect that to the figures that we're producing and displaying. So we're going to take 2 weeks to do this, and it's going to we do this at the end because of the final project. So we're going to put a lot of focus on the final project as a sort of a bow on the semester. So that's where we're going today. We're essentially talking about how to use the general linear model in various contexts. So we're going to cover a lot of familiar things, but from a higher level than we typically do. But before we do that, I wanted to just talk through homework 11. So this is going to, again, look different than the previous homework. What I'm asking from you from homework 11 is a single document. So you're going to start the framework for your final project. Remember, this is going to be very short. I'm not looking for a very long paper. I just need certain components. It doesn't have to be lengthy. In fact, it should be very short. So what you're going to do is, similar to homework 10, work through some of these questions, some of the pieces of a document I expect from you. And a lot of you are working in groups, which is great. When you work in a group, I want separate uploads for both of you, or all 3 of you, for the rare cases of larger groups. So everyone in your group should be uploading a document separately to Gradescope. It should have the name of everyone in your group, so both of you, and it can be exactly the same file. You don't have to submit separate files, just the same one. But I just need it to be, just for kind of completeness purposes, I need it from everyone in the group. But it's going to be, essentially the Gradescope submission portal is just going to be a one file upload. That's all it's going to be. I'm just looking for the document from you. So I just wanted to talk through sort of what I expect about with these things. So section 1, I just want your research question. So if I've been able to give you feedback on your question from homework 10, you can use that to inform how you structure your research question in section 1 of the paper. And as you're talking with your group partners, some of you have just paired into groups, so hopefully you've gotten that email. If you're in a group, have a conversation with your partner beyond what you did for homework 10. Just sort of refine the thing you're working on. Again, this doesn't lock you into anything. So what you submit is not a binding agreement that's what you're going to work on. But this is just a way of pushing your project forward in a sort of structured way. So when you're writing your question, be very specific. How does your question relate to the data set that you're using? And how is it sort of deliverable using the variables that you have? And then a lot of you are working with economic theory questions or, policy type questions. If there's a connection to economics, try to write about it. Like write a sentence about the connection between what you're doing and what we do in economics. Economics is incredibly broad. So it doesn't have to be, in fact, like almost none of you are going to be trying to estimate price elasticity of demand. It doesn't have to be economics in that way. Economics, if you try to ask what economics is, everyone's going to give you a different answer. It's a very broad field. So if it involves decision making in some way, it's going to be economics. And I've looked through almost all of your projects, and they're all connected to economic theory in some way. And then try to be feasible with the question you're constructing. This is a 100 level class. Imagine yourself with training wheels still on. We're not trying to make groundbreaking findings in this class. You can if you like, but often what I see is students trying to be very ambitious with projects like this, and I just don't recommend that. Treat this as like a practice round. So the next time you try, you'll be better at it. But don't try to overwhelm yourself with something that's very difficult. Remember the scope of what we're doing. So for section 2, I just need sort of a description of the data and sources. So describe your variables, the name, the definition, and then what do the numbers represent? So some form of units. If you're doing data cleaning or transformations, mention what you're doing. So I have a student who's using like a ratio of two different things and then taking a transformation of that ratio. So what he's going to do is just describe that transformation. So how he's transforming the variables. And then for the most important variables, I'm looking for descriptive figures. So this could be histograms or like a bar chart, depending on the variable, or it could be box plots. We've talked a lot about how to display variables in parts 1 and 2. So just describe the most important variables in your data set. And then section 3 is where we start building up the main part of the research program. So so we're using data to try to visualize the main question. So you'll have like one or two main figures which allow a reader, or yourself at this point, to try to understand what the data is saying about the research question. So often this is like a scatter plot. I'm going to show you a bunch of examples of this today. But this is often a scatter plot, but it could be other pictures. Like a two-sample t-test could be, a difference in means. So you could show two box plots with a line between them. So clearly label what's going on in your figure, and be appropriate using parts 1 and 2 of the class. And then the last 2 parts are just, you're trying to develop your statistical model. So you have a question, you have some data, and now you're trying to construct the correct statistical model. We've spent just like all of parts 3, 4, and 5 talking about how to do this. And we're closing that out today. Talk about which is the predictor and which is the outcome variable. You'll often have multiple predictor variables. So you'll write out your statistical model, and then you'll run your regression and present the results simply as a table. And then the last part is just interpreting. So how do you translate a coefficient from your statistical model into something that you can communicate in English? So if someone doesn't know anything about how to run a statistical model, how do you say the results in a way that makes sense? So that's a big part of what Section 5 is doing. Okay, so this may look like a lot, but once you get started, this will be hopefully a useful framework. And homework 10, you've done a lot of this work already. So this is really restructuring what you've already done so that it can fit into the structure of the final project. Okay, any questions about this? If you do, please feel free to stop by office hours tomorrow. I love talking about these projects. We've done a lot of work this semester, and this is really where it's going to start paying off. So, so hopefully this is fun for you. Students in past semesters have enjoyed this, so I hope this works for you too. All right, so what we're doing today is talking about many different applications of the general linear model, all in one sort of one breath. The general linear model is incredibly flexible, and what it allows us to do is approach many different kinds of questions with the same fundamental framework. We're thinking about the distribution of sample parameters, sampling error, and the t-distribution. And what the general linear model allows us to do is think about relationships more broadly. So we're going to go through 6 examples today, and I'm hoping to get out. I'm hoping we finish before the end of like the regularly scheduled class time, so that those of you who are interested in talking about your final projects, we can have a little chat before we all have to take off. So I'm hoping we can get through this quickly, but we should spend enough time on this to get the point across. So what we're doing today is focusing on turning a research question into a data source. So how do we go from research question to data source? Then how do we go from data to statistical model? And then how do we interpret the statistical model? And often this will involve visualization. But this is kind of the main approach I recommend as you work through this final project. And we're going to do it 6 times. So the first question is, or the first example is about a research question involving microlending. So you give out small loans in developing contexts with the hope of increasing flexibility with like investment and opportunity, which the aim is usually to increase monthly income or some measure of well-being in some way. So if you're seeing this question, and I do want you to answer these questions, what data set would you go after? Like, what would be the structure of a data set you'd be looking for if you were trying to answer this question? Imagine this is your final project. What data do you need? So let's maybe take like a minute here. I want you to, do you want to give compliments? Do you like giving compliments to each other? Either give a compliment or tell someone next to you what you're going to do for fun this weekend, and then what data source are you looking for? Like, what are the variables we would need to be able to answer this question? Take about a minute. All right. Anyone have any ideas here? There are a couple of ways of doing this, but I'm interested in what you came up with.
I said you need obviously the income data,
Okay, income.
and then you need the what are you gonna categorize that as by the community for low income, so you only get low income communities,
Okay.
and then you need a binary variable of if they have a microloan program or not.
Okay. So yeah, so one way of going about this would be to look at, families in low income neighborhoods or communities or wherever we're looking. And and then we'd have monthly income. And then we would have a second column, which would be whether they were treated with a micro loan. So we'd have a continuous variable as our outcome variable, and then a binary predictor variable as our treatment. And this would be one way of doing it. And then we could construct a two-sample t-test to be able to do this. A second approach is what I have in the slides, using what we call panel data. So we've talked a bit about panel data, but it's essentially paired observations. So this is the structure for what I'm going to show you. So we have 2 observations per household, and these are all households that are treated. So we have a household that's, we have their income before the treatment, and then a household, the same household after a treatment with a microloan. So we have 2 observations. If we're using this data, how might we show the main question? If we were to take 2 observations per family, one before and one after, how might we show this visually? What if we use, yeah, Luke?
We use some sort of like scatter plot.
So we could use a scatter plot, maybe even like vertical scatter plots with a box plot, both pre and post potentially. So that would be one approach. The other would be to show the actual pre and post average income with a line. So we have a bunch of families. Let's just plot the line graph for their household income across time. So maybe something like this. So here we have, on one side we have, on the vertical axis, monthly income. And then on the horizontal axis, we just have a measure of time. So we have our before period and then our after period. And these are just, each of the individual households represented by a line connecting their monthly average income before and after. We talked about a figure that looks a lot like this when we introduced panel data in part 1 at the very beginning of the semester, but that was a long time ago. So what this shows is the change in income before and after the impact of microlending. And then our second graph here is just the difference in monthly average income after the treatment. So after you got the microloan. And then this is just a histogram over those differences. Okay, so if we're thinking about how to set up a statistical model to test whether a microloan is effective, how might we write down that model? So I actually want you to try to write this model down. So we're going to use this visual, and then I'm on the screen. I'm going to show a statistical model, but I want you to get there first. So let's take maybe a minute or two to write down what you would expect, or like if you were trying to test this question using this data, what would you use? What statistical test would you write down? So let's take actually 2 minutes here, maybe a minute and a half. check with your neighbor, talk about this for a second. This isn't trivial. Like, these are the kinds of things we do. So try to write this statistical model down. Go. Okay, someone help me out here. Anyone have an idea? Well, we're trying to test whether the difference is different from 0, and specifically whether it's positive.
Do we use two-sample t-tests for this?
So if we were using the original data where we had just one column representing income and then one column representing whether the group was treated or not, we could use a two-sample t-test in that case. So in that case, it would be, our outcome variable is equal to, beta 0 times the treatment. So beta 1 times the binary indicator variable. But in this case, it's going to look a little different and actually kind of simpler. So it will be, some version of a regression model, which a two-sample t-test is a version of a regression model. I'm going to say this is a intercept-only model. We're going to try to test whether the difference is actually different from 0. So it would just be this thing, just a paired sample t-test. So we're just testing whether the change in income after this treatment is different than 0. So then we could check beta 0 and whether that was different from 0. And we could do that all in the regression framework, just testing, just checking the p-value. Okay, any questions here? Anyone write this down? All right, so this is our warm-up question. This actually might be one of the more difficult ones. But the interpretation here is average monthly income increased by beta 0 on average from the program. And then if we get a p-value, which we would if we ran this regression, we would say the interpretation here is that we would expect to see a result as extreme as beta 0 under the null hypothesis only p% of the time. So whatever that number is, that would be our the probability of seeing something that extreme. And then the more standard way of saying this is that we would reject the null beta 0 is equal to 0 if our p-value is less than 0.05, or whatever our critical level is. This interpretation, as we've talked about a couple of times, has some problems with it broadly. So I prefer to talk about p-values in this more technically correct way. But this is sort of the standard way we talk about them. So it's good to know that too. Okay, any questions here? So that was a warm-up question. We're going to do, 5 more. So our second example is about online learning effectiveness. How many of you were in, I guess a lot of you were probably in high school during COVID, right? And you had like online high school classes? Anyone like those? I taught some classes during COVID, and I found it very unpleasant. So one question we might have is whether online classes are as effective as in-person classes. So if we have that question, we would need some data to be able to test it. So if you were thinking about the data structures or data sources you might be interested in using to test this question, what might they be? So let's take about a minute here. We're doing this 6 times because this is the practice. We ask a question, we look for data to answer that question, we construct a statistical model to be able to answer that question with our data, and then we try to interpret what the model is telling us. So we're going to do this 6 times because this is the process. So let's take a minute here. Let's think about the kinds of data we might need to answer this question. Go. Okay, someone help me out here. Let's think about this in detail. What data would we need to answer this question? Yeah, Luke.
Grades or scores.
Okay, so some measure of grades or like performance in a class. And then what else? Ben. Yeah, so like a binary indicator variable of which group you're in. So we have 2 groups, and we're going to try to test whether they're different. And we could be a little more specific here. So we could say these are, standardized test scores. So like a final exam. And then hopefully the class is the same. So it's like the same instructor, same questions in both of the 2 groups. And the only thing that's different is that one is in person and one is online. Okay, so if I'm seeing this data, what I want is a box plot with a scatter plot. So I'll have a question for you about these figures in a second, but this is the one I would start with. So I have 2 groups. I have the online group and the in-person group. And then I'm just going to construct a box plot with the scatter plot behind it of the test scores in the 2 different groups. And then I also have 2 histograms stacked on top of each other on the side, just to show the distribution of scores. How many of you like the box plot better? How many of you like the histogram better? Oh, interesting. Wait, hands for box plot again? And then hands for histogram? Oh, interesting. I definitely prefer the box plot. Why do you all, those of you who answered histogram, why do you like that one better?
Just back into the Instagram over the online one, it makes it easier visually to compare.
So they're like, in the same area, where here you have to sort of look left and right.
I guess, yeah.
Yeah, maybe. Yeah. This is one of those things where there isn't really a correct answer. Often the way of communicating figures, as you'll find out with your final project, it's really a matter of taste in a lot of contexts. Personally, I think this is a clearer communication of the data. But if this is easier for you to interpret, then maybe that's the right one. I've included them both for that purpose. Okay, so if you're thinking about the statistical test, this is the main question here. How do we translate our data and our question into a statistical test in the general linear model framework? So I want you to take a minute or two here, write this down, and then check with someone next to you. This is one of those classic tests. Go. Okay, someone help me out here. What model are we writing down? Okay. And what type of t-test? So a two-sample t-test. We have two groups, and we're trying to test whether they're different. How do we write a two-sample t-test as a general linear model?
I mean, I can't. There's a beta 0, is beta 1, which would be online, would be the first, and then B2 would be in person.
Okay, so we have our beta 0, which captures our baseline test score, and then we have our beta 1 times the indicator variable for whether you're in person or online. We could include another one, but that can make things messy. So this is actually what I have written down, which is very similar to Frank's idea here. So this is our two-sample t-test. We have our beta 0, which captures the baseline test score for the group that's coded as 0 in online. So if online is 1 for online learning and 0 for in-person learning, then beta 0 captures the average test score for the group that's in person. And then beta 1 times online, just beta 1 captures the difference between the two groups. So in this case, if online learning is not performing as well, then beta 1 we would expect to be negative. Okay, any questions about this? This is our two-sample t-test. And then what we would do is interpret the betas. So beta 0 in this case isn't so informative. It doesn't directly relate to our question. It would just be the average for the in-person group, and then beta 1 would just be how many points higher the in-person group scored. Or another way of saying it is, I mean, if beta 1 is negative, then it would be how many points lower the online group scored. And then we would interpret the p-value in the same way. It's just, the probability of seeing something as extreme or more extreme than the sample that we've observed. But the more classic way of saying this is that the difference is statistically significant if the p-value is less than 0.05. Okay, any questions here? This is the correct way of talking about p-values. This is a convention that we've arrived at, which has led us to some problems. If you all know about the replication crisis, it's sort of related to this. But it's just sort of, we have a certain level of confidence that we want for us to reject a null hypothesis. But the correct way of understanding the p-value is more similar to this. As we've talked about the intuition. It's like the probability of seeing our sample given that the null hypothesis is true. So if the p-value is very small, then we're saying it's very unlikely. All right, how about example 3? So one of my students last semester actually did a project very similar to this. He was wondering whether there was a relationship between renewable energy investment and carbon emissions. So the first step, as always, is if we have a question, what kinds of data would we need to be able to answer this question? So we've gotten through 2 warm-up questions. Here's our 3rd one. And this one's actually a little, there's going to be a nuance to it. So be thinking about what that might be. What's the relationship between renewable energy investment and carbon dioxide emissions across countries? So we're going to compare different countries and their variables related to this question. So let's take maybe a minute here. This one might be more straightforward based on just the statement of the question, but be thinking about whether there are confounding variables, like we talked about last class. So let's take a minute here. I want you to write down some variables you might need for this question, and then potentially other ones to help avoid some confounds. So we'll take about a minute. Let's go. Okay, someone help me out here. If you're still talking, that's great. Keep doing that. What data sources might we be interested in? Corey.
Carbon emission data.
Okay, so some measure of how much each country is emitting. And what else? Luke.
Like data that includes like their energy investments and GDP as well.
Okay, so we have our 2 main variables. We have carbon emissions and we have renewable energy investment. Luke is also pointing out that maybe we need something else like GDP. And why might we need GDP in this case?
It's like maybe something like GDP and population as well, because like a country could just they could have high investment, but they could also have other like factors as well contributing towards carbon emissions, like population, like stuff like that.
Yeah, so like
there could be like multiple other factors that can contribute to their carbon emissions.
yeah, so a large country could just have very high carbon emissions simply because they have a lot of people.
Mm-hmm.
And so we want to sort of disentangle that. Someone mentioned GDP. Was that you, Courtney, or Luke? So so population might allow us to think about like carbon emissions per capita or something along those lines. Yeah.
Getting to a GDP question, I was thinking it could be a way to make like your renewable energy investment like a weighted score,
Okay.
like rather than just like renewable energy investment, because in the same vein of like you can just have like a large country with like tons of carbon emissions, you could have like a large sum of renewable energy investment, but if it's tied to like a huge country,
Yeah.
it's like I don't think it's like as comparable.
Yeah. Right. So a large country, whether that's population or GDP, is, I mean, a large country just has more money to spend on investment. So if we could think about maybe renewable energy investment as a percentage of GDP, which might be a better measure. Yeah. We can also use GDP as a control, as a statistical control for like the wealth of the country. So we can use GDP in a lot of ways. So this is probably enough to get started. This is a pretty complicated question for a lot of reasons, but this is at least a place to start. So let's say we have 50 countries. We have renewable energy investment, and let's say this is, as Luke is suggesting, a percentage of, let's say, GDP, but it could be per capita if we wish. Then we could have carbon emissions per capita, so it's tons of carbon per person. And then let's have a separate variable for GDP per capita. So if I'm thinking about where to start with this question, where I'd go to first is a scatter plot. We have a bunch of continuous variables, and what I'm going to do is just scatter each of these. I'm going to do this in a little more complicated way, using colors. This isn't something we've relied on a lot this semester, but I wanted to show you this and talk it through. So the first one, we have renewable energy investment as a percentage of GDP on the horizontal axis, and then we have carbon emissions as tons per capita on the vertical axis. And so you can clearly see that there's a positive relationship between these two variables, like our main variables after we've normalized them for like size of the country and size of the economy. But you can also see I've added a color to the different points on the scatter plot. The closer they are to yellow, the higher the GDP per capita is, and the closer they are to purple, the smaller the GDP per capita is. So this is like a measure of how wealthy the country is, independent of the two other variables. And you can see there's, like behind the scenes, there's this positive relationship between the wealth of the country and both renewable energy investment and carbon emissions per capita. So it's like wealthier countries give us, invest more per capita in energy, in renewable energy. But wealthy countries also burn more carbon dioxide. It's like if you have more money per capita, you're just going to burn more per capita. So if we're thinking about a confounding variable, we might, even if there isn't a relationship between renewable energy investment as a percentage of your GDP and carbon emissions, we could still have a relationship between these variables, even if it isn't direct. It could be going through GDP per capita. And so what I've done here on the side is actually just include a statistical control for GDP per capita. We haven't talked about these partial residual plots, but essentially what this is doing is showing renewable investment after we've controlled for GDP. And then I've done the same thing on the vertical axis, showing carbon emissions after controlling for GDP. And then I've just plotted these two things together. So if you were thinking about trying to deal with all of these problems at the same time, we have this potential confounding variable of GDP per capita potentially impacting both our predictor variable and our outcome variable. How might we did something almost identical to this last class. How might we write down a regression equation to get at this problem? our general linear model. Let's take maybe 2 minutes here. I want you to try to write this down. Take a shot at this, write it down, and then check with someone next to you, and then we're going to do it on the screen together. Go. Okay, someone help me out here. How might we write this model down? What are some of the pieces? Incorrect answers only. Someone give me a wrong answer. Is a wrong answer easier or harder than a correct answer? Harder? You would give me an easier.
Your outcome variable is carbon emissions.
Okay.
That would be your 0.
Yep.
So like your base carbon emission without any input or like investment.
So nice. So we have carbon emissions per capita is equal to beta 0.
And then plus E1 renewable investment.
Okay.
And plus E2 GDP per capita.
Okay, so we have 3 things going on. We have our outcome variable, which is our vertical axis, our y variable. We have a beta 0, which captures the baseline carbon emissions per capita across the countries. Then we have a beta 1 on renewable energy investment as a percentage of GDP. But then we have a beta 2, which allows us to control for GDP per capita. So this compares 2 countries with the same level of income per capita, or GDP per capita. So we're comparing the same same wealth countries to each other. A terrible sentence, but you get the point. So I would say it looks like this, which is almost exactly what Aiden wrote down. And then we include our epsilon term at the end, which just it tells us that the equation actually works by allowing for there to be difference between the model and the data. Okay, any questions about this? And Aiden even went as far as to interpret what beta 0 is doing. It's just the baseline carbon emissions when each of the other values are 0. So the way I would interpret this, we would say each 1 percentage point increase in renewable investment is associated with a beta 1 change in carbon emissions after we've controlled for GDP per capita. So this control allows us to compare 2 countries that are equivalent. Okay, and then we would talk about the statistical significance here. And then we could even interpret GDP per capita on carbon emissions with beta 2. And we'd all expect this to be positive. Okay. So example 4. Let's go through this a little more quickly. We've already done this in class, so I just want you to remind yourself of the process we walked through when we tried to answer this question. So let's say we're interested in the gender wage gap across educational levels. So does the gender wage gap vary with educational level? So our research question would be, are there different returns to education by gender? And so what we could do is just collect data. We would need hourly wage, we would need gender, years of education, and then I'm going to throw in experience here. You can't actually easily find experience in census records, so this is a little bit harder to get access to. But if we have it, we can perform an additional statistical control. So this is the picture I would start with. This is the one we worked with when we did this in class. Just horizontal axis is years of education, and then the vertical axis is your wage or some measure of income. And then we can plot two different groups. So the two gender groups that we have, and we can just plot them separately. And then we have our lines running through each of the two groups we're considering, and we can test whether our statistical model shows a difference in the slopes of the lines. And so what we can do is essentially construct a statistical model that matches the possibility of these two lines. What's powerful about these scatter plots is we can have two different groups on the same figure, showing potential differences in relationships. So what I've done here, I have wage, so our vertical axis, I have beta 0, I have beta 1 times education. So this is the slope of our baseline group, which is the 0 for the female category. So this is the male line. And then we have our interaction term. So this is female times education. So this is the slope that's different for the female group. So the difference in addition to the baseline slope for education. So that would give us our beta 2. And then what I've also done is include a statistical control, because maybe there's something going on with experience that's different. So we could talk about different stories for why we might want to include the statistical control, but we could. Okay, so then the interpretation, essentially beta 1 is the base gender gap for, actually this is not right. Beta 1 in this, I changed the regression equation and didn't change these. Who wrote these slides? Yeah. Someone got into my files. No, I just forgot to update them. So beta 1 is actually the returns to education for the baseline group. Beta 2 is the interaction. So this is the additional returns to education for the female group, which in general, we expect this, we found in the census records that this is actually negative. The way we did it in class, this was, we used male as the indicator variable and found that beta was positive. But here, because we're using female as the indicator variable, we'd expect it to be negative. And then beta 3 is the returns to experience. So after we've done our controls for experience. All right, so let's turn to example 5. Should we try to get out of here early? Actually, we're not going to get out of here early. We're going to end the slides early, and then we're going to talk about the projects. I want to have a conversation with as many of you as possible over the next couple of weeks, either in office or in here. And we're going to actually structure our class around that objective. So one question we might ask, I own a house in Pittsburgh. I also ride a bus almost every day, and I like parks. So one question we might be wondering is whether better access to public transit and proximity to parks is related to the price of a house. When I was buying a house, I was on Zillow just constantly. Do y'all get on Zillow? just for fun. Yeah, like whenever I'm traveling, I get on Zillow and just check. I was in Montreal over the summer and was looking at the house prices there. I'm never leaving Pittsburgh, but it's just fun. Y'all know the like they have a walkability score. It's like how walkable the neighborhood is. There's also a transit score, so like how good the public transit is. Did you also know Zillow has a Python API? You can actually interact with Zillow data using Python. I played around with it a little bit in grad school, but you can get like house prices, walkability scores, transit scores, all of these things. You just interacting with code. You have to like get an access key and all of that, but you can do it. And I actually had a student last semester who did this. He constructed from I'm not sure if it was the Zillow API, but he interacted with an online database using Python to get access to prices and use that for his project. So one thing we could do here is get access to those kinds of values. So let's take maybe a minute here. I've given you some indications, but there's one more. Like we haven't talked through all of the variables we would need for this project. So let's take a minute just to talk about the data and the structure of the data that we need to be able to answer this question. Go.
No, that's fine. I mean, like, I had the answer. So if it was something more difficult, I would have been like, man.
Yeah.
Yeah,
No, I ready to answer it.
So you jumped on it. Yeah. All right.
Yeah, sorry about that.
I feel like after maybe a minute of dead silence, you can just like pick on whoever. You did it to yourself.
Yeah, maybe I'll just call it myself next time. All right, someone help me out here. What kind of data do we need? Like, what are the variables that we need to be able to answer this question? I've given you a couple already. So price, we could get that with the Zillow API or some other database. What else? Transit score. We could also get that with the Zillow API. What else?
I don't know if it's excessive, but you can also get information on, say, access aid on like how the public transit access and green space proximity have like improved over those decades, and then also compare that to how property values rise over that decade. It's a little.
Oh yeah, yep. So it's a little more complicated, right? We'd have to do like a difference model to look at, like 2 periods, and then make a comparison, prices, how prices have changed, and then also how the value themselves have changed. So we could do it, but it'd be a little more complicated. In addition, like if we weren't doing the difference model, what else would we need? I think we'd need at least one other thing.
Like the distance from a bus stop or how easy it is to get to both buildings.
Yeah, so Zillow does something like this, I think, when they construct their transit score. It's like how many buses are going through the area, but we could construct it directly ourselves if we wanted to. So like distance to the nearest bus stop, weighted by like how frequent the bus comes through or something. Yeah. What's one other thing? What about proximity to a park? So let's say we could either construct like a measure of meters to the nearest park, or we could construct a binary indicator variable for whether a park is within like a quarter mile. So we can do it a couple of ways, but we need some measure of proximity to a park. So this is maybe what I would use. The last thing we should think about is a confounding variable. So prices aren't just directly related to local amenities, but also to the quality and quantity of the house. So one of the best predictors of sale price is actually square footage. So we could throw that into our regression as a statistical control. And we need to, for a number of reasons. Let me show this picture here. So in both of the figures, we have price on the vertical axis, and then one of the two measures on the horizontal axis. And then we've broken the scatter plot out by proximity to a park. The horizontal axis for this first one is square footage. And you can see the price of a house. I mean, this is synthetic data, but this is approximating the truth. Square footage is very closely related to price. Large houses are not typically near bus stops. The better the public transit, the more likely the house is to be small. So if you have a large house, it sells for a lot, but it's probably not in an area with great public transit, just in general. I think Shady Side is maybe an exception. There are lots of very large houses, and transit is pretty good. But in general, there's a negative relationship between these two things. So we would need to control for house size if we're trying to get a good picture of the relationship between price and transit score. So the regression I would run, I would try to predict price using beta 0, so the baseline price, and then I'd try to control for the quality and quantity of the house, so how big the house is, a great predictor of house value. And then we could throw in transit score here. So is transit score related to the price of the house? So when we're comparing two equally sized houses, is one in an area with better transit selling for more? And then we could also include this beta 3 on green space, which would give us, is there a difference between the green and the blue group? And I would expect that there would be. Okay, any questions about this? So this is how we would run this regression. And then this is how we would interpret these things. Almost exactly as I've said already. So we have beta 1 price increase per 100 square feet. Beta 2 is for every unit improvement in the transit score, how does the price go up? And then beta 3 is just the green space premium on a house. So how much are people extra willing to pay for a house that's near a park? Okay, so last one here, and then we'll talk about projects for a couple of minutes. So if I were interested in how the retail sales vary by season after we've controlled for baseline trends, what I would be looking for is some measure of sales. And then I would want to know the quarter. So like which of the 4 quarters is the sales in. And then I'd also want to pick up the trend. I'd also want some measure of like time since the beginning of the time series. So the way I would write this would be something like this. We have sales, we have the time trend, and then we have seasonal indicators. And we talked about this last week, but we could construct a picture that looks like this, like a time series graph by for sales. And then I've also colored in the different quarters behind the scenes. And then I've separately aggregated sales by quarter. So instead of plotting this over time, we could just plot by quarter, averaging the different groups. And the way we would run a regression to get the average sales by quarter, after controlling for the trend, actually, let's take 2 minutes here. I want you to write down a regression equation that you think might be able to capture this thing. There are a couple of ways of doing this, but let's attempt this. We'll take 2 minutes here. Write it down and then check with your neighbor. This is Oakland, after all, the neighborhood of Mr. Rogers. This is truly Mr. Rogers' neighborhood. Didn't know that? Mr. Rogers' neighborhood was filmed like half a mile from here.
Also, I like passed like a sign, I think on Juliet Street that said Cuomo.
Yeah.
I knew like he was from Pittsburgh, but not like
Yep. I think he grew up in South Oakland.
Yeah.
Bless you. You're welcome.
Yeah, it wasn't quite a snake plus, not quite anything else, so.
A snick up.
Yeah, maybe.
Okay, someone help me out here. What might you write down to test, to like control for, seasonal effects and the baseline trend? Because it does look like there's maybe an upward slope here that's really noisy, but you can definitely see there's higher sales in the months in, what's that, quarter 4? So like holiday season. And that's very consistent across the different years. So how might we deal with all of these things? Taylor. Oh, so the way I would write this, I would set sales equal to beta 0 plus some time trend. So like how many months or how many quarters after the beginning of the time series. And then I would include indicator variables for the quarters that are not our baseline. So we could do this in a couple of ways, but I would include maybe quarters 2, quarter 3, and quarter 4 as indicator variables and just include them separately. So that would look something like this. So we have sales is equal to beta 0 plus beta 1 times time, beta 2 times Q2, so this is just an indicator that the sale is, or the month is in Q2. Beta 3, it's in Q3, and so on. And then we have our epsilon term just to show the difference between the model and the data itself. Any questions here? All right, so this is sort of an interpretation of each of these betas. We've already kind of talked through a lot of this, but beta 1 is the time trend. So how do sales go up? And then the beta 2 through 4 are just the seasonal effects. And the main idea here, as we talked about with time series, is we want to be able to control for time varying things, but we also want to control for seasons sometimes, particularly with data like this, like sales. There tends to be strong seasonal effects. And so we want to be able to quantify those things. So we've gone through 6 examples, 6 different ways of using the same flexible model. These are just, this is like a framework slide you can potentially use. These are just variations on the same underlying idea of sample error with a sample parameter that follows a t-distribution, which we can make claims about because of the central limit here. So each of these parameters, each of these betas, gives us a different, slightly different distribution. We can do all of this simply using the sample. These are the main specifications we've talked about, the main models. But in all likelihood, you're going to encounter, if you keep using statistics in your life, you're going to encounter models that are not on this list. You're going to have to construct your own model. This general linear model is a framework that allows us to do lots of very flexible things. You've seen t-tests and you've seen regression typically in separate sort of modules in your statistics class. They're the same model. And what I've written out here is how they're related. And it's not just those kinds of models being related. It's that we can extend this basic framework, the general linear model, to really any kind of framework we can think of, if we can draw lines connecting points on a graph. So to me, this is just an incredibly powerful tool. I wrote my dissertation using a general linear model that I constructed. It's like not on this list. You may encounter a problem that requires you to construct something that's slightly different than what you've seen on this list. What I'm hoping you get from this class is the ability to flexibly implement a general linear model to be able to answer your question. It's incredibly powerful. Okay, I've said that like 14 times this semester, but this is sort of a unification slide. So when you're going through your project, I want you to think about what your research question is, start there, and then use that to sort of guide the model selection. We started with a question, and then we went to the data, asked what kind of data we might need, and then visualized it. And then once we had the data, the visualization, we could then match that to the model itself. So we took the data, the visualized data, and then constructed a statistical test using the data we got from our, guided by our research question, to then be able to construct a statistical model for that data itself. And then from there, knowing how sampling error works allows us to interpret what the coefficients and the p-values truly are telling us. So it's that interpretation, taking the printout of the model and turning that into something that we can say in English, that's an incredibly powerful skill in itself. Okay, so this is the end of like the main part of part 5. We've done this 3-part progression, part 3, part 4, and part 5 to get to this point. From here on out, we're going to be talking about sort of all of these parts in sort of a unified context. We're going to be thinking about how we present research, having gone through the first part 5. So feel free to stick around if you have questions. We actually ran out of time. So we're going to spend more time in class talking about projects. I will see you all at the McKay lecture or on Tuesday or tomorrow, office hours tomorrow morning.
I wanted to ask
I know before we spoke on, so I'm working with my project with someone in the other section.
Okay.
And I
Oh
told
yeah, on is it?
Ian.
Yeah, so like the baseball score,
Yeah,
the
yes.
baseball stats.
So I was
Yeah.
gonna ask,